Welcome back, everyone. Mr. LaRusso here again. Today we are on the third note regarding vectors and scalars. In this one in particular, we're going to be dealing with a new method for solving vector questions called the component method. I think we should circle back to that last homework question that I gave you. You remember the one. This one where we had three vectors that we had to go through. So our vector A, our vector B, and our vector C. If you recall, with that question, the solution was absolutely awful. Yeah, look at that. It was all that. Yes, look at all that algebra. The diagram, though. Oh my goodness. Like, who needs this? So again, as a reminder, this is what I defined as sadness, teary eyes. So this was quite the emotive, very sad, like, good gravy, what am I doing here kind of question. And the reason being is that there were so many steps. So many very sad steps that you needed to go through to solve this question. Okay, goodbye to our little emo mascot there. And it all came down to how unmanageable, or maybe not unmanageable, but let's not exaggerate things, but how unnecessarily complex it turns out that this is. And the reason why we had to go through all these steps is because currently we only know how to work with triangles. As it turns out, though, you can turn any hot mess, such as this, into a triangle. Allow me to demonstrate. Okay, so I've moved off to the side here to get a little bit of real estate, and we've got a grid going on here. So what I'm going to do is I'm going to draw just a couple of random vectors. So here's our first vector, and we'll have that one in blue. Here's a second vector. Now let's make that one in green, and then we'll add a third vector, and how about purple? Purple will work. So here we go. We have three non-collinear vectors. And let's say we want to find the resultant of vector blue plus vector green plus vector purple. Now, that resultant is going to start at the tail of our blue vector and go to the head of that purple vector. So just making the lines a little bit thicker in this case. All right, so now, normally I draw my resultants and whatnot as dashed lines. The only reason why I'm not doing that is because one note makes it hard to move a line once I've made it a dashed line, because it's a bunch of little lines. Anyway, it doesn't matter. Just pretend our red resultant is the dashed line. We can do that later. It's not a big deal. All right, so now solving this problem is very obviously not going to be fun. It's actually probably even less fun than the last question we did, because look at these ridiculous angles over here. Like, come on. Like, the resultant crosses over. Nobody's got time for this. Nobody. All right, so here's the idea. You can actually take any vector and break it up into the sum of two or more vectors. Hear me out. The number 3 can be broken up into any combination of numbers that, so long as they add to 3. So for example, 2 plus 1, or 5 plus -2. These are all examples of possible numbers that we can add up to make 3. Vectors do the exact same thing. So far, we have just added vectors together to make a single one. So we've taken a bunch of vectors, combined them, and then turned them into a single resultant. You can actually go the other way too. So just a little concept. So let's say you had one vector that was going this way. Make that a little thicker. And then you had another vector coming up like that. Your resultant is this right here. And here, I'll just color it red so we recognize that it's resultant. I'm going to argue that you could actually do the reverse. You could take this vector and then break it up into an alternate path. And it works because the start point and the end point are identical. It's the same spot. So it doesn't matter what route you take to get there, as long as you get there. As long as the starting point is the same and the end point is the same, you can actually replace any vector with a number of other vectors, so long as they all add up to the same thing. So now we're going to put that theory into practice with this example that we have here. I'm going to start off with our blue vector. And what I'm going to do is I'm going to move it out of the way for a moment. And what I'm going to do with this blue vector is I'm going to break this up into two pathways, a route along the X and then a route along the Y. So I went x, then y. So if this is vector blue, this would be blue x, or bx, and this would be b subscript y. So this vector b is equivalent to this bx plus this by. Again, big idea. Starting point, end point. So either we take this direct route like we just did here with vector b, or we take this longer route. It doesn't matter. The result is the same. So now what I can do is I can actually put back these vectors as a replacement. And if you look, it did the exact same job as our blue vector over here. It got us exactly where we needed to be. We're going to repeat this process, but this time we're going to work on the green vector. So we draw the x component, then the y component. So if this is our green vector, this would be our x component of the green vector, and this would be the y component of the green vector. All right, so let's pull these aside here, and we're going to replace our green vector with our components. And of course, the last one we have to do is the purple vector. And we'll just do this one in place. There's the x component, there's the y component. Px, py, and there is our original purple vector over here. Okay, so these three vectors, let's just move them off to the side right now. Okay, so you might be saying to yourself, okay, that's great, that's awesome, but it actually looks like there's more work now. Hold up. There's also the concept that the order in which we do the addition doesn't matter. So what I'm going to do is I'm actually going to rearrange these, and I'm going to start with getting all the x vectors together first. So what I'm going to do is I'm going to shuffle them around, and I'm going to put my x component of my green vector over here, and then the x component of my purple vector. I'm going to drop that down over here. All right, so now we've got bx, gx, and px in the x-axis. Now we take on the y-axis. So the blue component of the vector in the y-axis, then our green vector, and our purple vector happen to be already in place. And, well, what do you know? Isn't this lovely? A right-angled triangle. That would be your angle theta, and there is your resultant r. And that's the big idea. What we can do is we can take any ugly vector question and break up every single vector into their x bits and their y bits. And then you just simply get a right angle triangle. Well, of course, we need to figure out how big the x side is and how big the y side is. And that's really simple too. So once we have these numbers here for all the x components and all the y components, your resultant in the x, so this cumulatively would be your rx. That would be equal to bx plus gx plus px. And then, of course, you would do the exact same thing, but for the y component. So that's all there is to that part. So conceptually, I think we all understand what's going to go on here. Once you figured out these subtotals over here, then you would find your actual resultant value by taking your rx plus your ry, and that would just be using Pythagorean theorem and tangent to find your angle. What I haven't told you yet is how you can find these bx, gx's, and px's, and these by's, gy's, and py's. Spoiler alert, you actually already know how to do this. You just don't realize that you know how to do it yet. So here we go with the component method. Let's say our first vector, we have a vector A, and let's say vector A is 30 kilometers, and its direction is west, 20 degrees south. Okay, so this is how you first of all sketch this diagram. Note, it says west first. So the first thing you do is you draw the western component. Next, you go south, and there is your y component. And that 20 degrees, that is always at the tail of your vector. So that angle theta, that's your 20 degrees right there. Again, let's recap that. So first things first, you start west, then you go south, and that angle, 20 degrees, is right there at the tail. So the easy part is getting the directions and getting that angle. No calculations yet. How, though, do we get that number and that number? Answer, SOHCAHTOA. All right, so now there are three parts to SOHCAHTOA. There's the sine, the cosine, and the tangent. We're going to identify which of these three that we're going to use to figure out what the x component and the y component are. And to do that, what I'm going to do is based on where theta is, I'm going to label each side of the triangle as opposite, adjacent, and hypotenuse. Let's start off with the easy one. The hypotenuse is always opposite the 90. So that right there is the hypotenuse. And if you look, we know the magnitude of that side. So right now we have an angle and a side. Next, from the perspective of theta, the opposite side is this side here. That's your opposite. And that means that there's only one side left, and that would be your adjacent side. So let's say, for example, we want to figure out what AX is. All right. So we're trying to figure out AX. So that side is unknown. What do we know? We know theta and we know the hypotenuse. Okay. What trig ratio involves adjacent, hypotenuse, and an angle? That would be cosine, of course. So here we go. Cos theta of vector A, I should actually put in subscript A down there. That is equal to the adjacent side, which is actually your AX, over your hypotenuse, which is just A. And of course, magnitude of the side. So small letter A over A like this. Now, technically, I should write it like this. That's technically the way you should do it. But for the sake of clarity, I'm just dropping the harpoons, which means that we're talking about the magnitude only. Okay, humans of profound awesomeness. We need to isolate for AX because we want AX by itself. Well, to get AX by itself, we have to do SAMDEB. So let's see. Nope, no subtraction or addition, but we have, no subtraction or addition, but we do have division. So we want to move A to the other side. So since A is attached to AX via division, the opposite of division is, of course, multiplication. So we end up getting A cos theta A is equal to AX, or AX is equal to A cos theta A. That's it. So you put those numbers in, and then you can find that X component of vector A. Okay, cool kids. Now it's time to find AY. AY is unknown. We have the hypotenuse. We have angle A. And technically, we have the adjacent side, which I gave an amber check mark. Why did I give it an amber check mark? Because the value for side AX is going to be sus. And the reason that is because there's potential rounding error or just good old-fashioned error. So if you can avoid using this, you're going to. So that being said, we now have opposite, hypotenuse, and an angle. That would be sine of theta A. And that is equal to the opposite, which is AY, over the hypotenuse, which is A. Doing the same math we did before, we do the opposite of division, which is multiplication. So we get A sine theta A is equal to AY, or AY is equal to A sine theta A. I'm going to be straight up with you. We're never going to be doing these steps. We're always going to start right there. So this makes things actually very easy. For finding your components, your AX and your AY, in this case, your AX is equal to A sine theta A, and your AY is equal to, oh, I'm a goof. Let's try that again. Hilarious. Your AX is equal to A cos theta A, because the AX was on the adjacent side. And your Y component is on the opposite side. So we know that is automatically going to be the sine function. And those are the only two possibilities. Either you have a cos or a sine. And here's the deal. If you know one, you automatically know the other. So if you know AY is the sine function, AX has to be the cosine function. That is always true, forever and ever, amen. Which makes these questions actually pretty simple, because all you have to do is figure out one of the sides, and then the other side, I should say, you already know instantly. So now let's organize the solution. So as you can see here in the note itself, which you can review later, I actually did go through the calculations for both cosine and sine. So now what we're going to do is we're going to look at this question that we had, this one that caused so much sadness. We're going to break this one up into the component method. So here's what you do. So we are looking for the resultant of vector A plus vector B plus vector C. What we're going to do is we're now going to break up each vector into their components. And to do that, we're going to make this vector chart. So here's how that looks. The column that says vector, that is where you're going to put your new vector diagram. Then the next column will be the calculations for your x component, and then your y component beside it. One of the most common mistakes is getting the order of the components wrong. So let's take a look at the first one. We know that it has a magnitude of 1 kilometer, but here is how you draw it. North first, then you go west. So you start north, then you go west. Let's sketch it out. Go north, then you go west. And as you can see, your vector A is north, 30 degrees west. As you can imagine, the most common mistake is this. No, bad human. And here's the reason why. Is because this angle, 30 degrees, is here, not there. Now, technically, you could find the complement here and solve it that way, but that's just stupid. It's a waste of time. So you're not going to do it that way. All right, so we're going to zoom in on this diagram. Now, we have the diagram established. And remember, we know that value and we know that value. We know the hypotenuse and we know the angle. And next, we have to identify which side is the opposite side and which one is the adjacent. So obviously, the hypotenuse is always opposite the 90. And from theta's perspective, this is the opposite and this is your adjacent. The y is your adjacent. Immediately, as soon as you see this, as soon as you see opposite, that's associated with sine. Adjacent, cosine. So the x component is sine and the y component, cosine. So next step, you substitute your numbers in and then you get the magnitude and direction. Now I want you to notice something. No harpoon, no harpoon, harpoon. Because in these two lines, that was just working with the magnitude, but in this last line, we have the direction. So get that notation right. Okay, so let's take a look at vector B. So we go west first, then we go south. West, then south. So if we take a look, west, then south. And there's your theta B. Since theta B is here, BY is your opposite side, BX is your adjacent. So that means the BY is now the sine and the BX is now the cosine. So you see how it can flip sides depending on which way your angle is going. You then substitute your values in and then you get your component in the correct direction. Finally, let's take a look at vector C. Now with vector C, there you are, up there. So vector C, we go south, then east. South, then east. And there's your angle. Again, we know the hypotenuse, we know the angle, and the opposite side of theta is your x component, and your y component is now your adjacent. So as soon as you see the word opposite, you know that that means sine. So CX is related to sine. And then of course, y has to be cosine. Then you substitute your values in, and you get your final answer with the direction. Don't forget your harpoons. Okay, so now it's time. Now that we've got all the x and y components, now we have to find our subtotals. We have to find our resultant in the x and then the resultant in the y. So basically, we have to combine these three with themselves and then these three. But you have to be very careful. And I'm going to highlight some things. West, north, west, south, east, south. Notice that in this column here, everything's on the x-axis. And in this column here, everything's on the y-axis. So I want to make sure we understand very clearly that west means negative. That would be negative as well. Negative. No, what am I doing? That's east. Good gravy. East would be positive. There we go. Now let's take a look at the y component. This first vector component, it's going north. That's positive. The second component, that's going south. Well, that's negative. And the third component is also going south. That's also negative. And that gets reflected in our vector equations down here. So notice, you start off with your raw equation. So that is vector Rx plus vector Ay plus try that again. Vector Rx is equal to vector Ay plus vector Bx. All right, third time's a charm. vector Rx is equal to AX plus BX plus CX, all vectors. Apparently saying the word vector was tripping me up. So this first line here is in vector notation format. Now we drop the harpoons and then we substitute our values in, making sure that we identify with the correct sign. So AX, that was west, so that made it negative. BX was also west, which made it negative. And CX was east, that made that positive. So your subtotal is going to be negative 2.032 kilometers, or take that negative and convert it into west. Okay, so there's your Rx component. Now we look at the y. Again, vector Ry is equal to vector Ay plus vector By plus vector Cy. And looks like I have to edit my note again. There's not supposed to be a harpoon up there. Oops. All right. Well, regardless, Ay was going north. That's why it's positive. But By and Cy were going south, so therefore they're both negative. Therefore, the magnitude of Ry is equal to negative 1.788 kilometers. Putting it back into vector notation, dropping the negative and turning that negative into south. And that's because we're on the y-axis. So on the y-axis, positive is north, negative is south. On the x-axis, east is positive, west is negative. So the final stage is we now have to make our what's called our new vector equation. So we have Rx and Ry. So now our resultant is actually just the sum of Rx plus Ry. Now technically you could do Ry plus Rx, but I usually do almost always Rx plus Ry. Only reason why? Alphabetical order. I didn't say it was a good reason. So here we go. We start off with our new vector equation, and that is vector R is equal to vector Rx plus vector Ry. And when you draw the vector diagram, you have to draw in the order in which you label them. What that means is the following. Since Rx is first, you do Rx first. So Rx was to the west. There's my Rx. Then followed by your Ry, which was south. And this is your resultant. And the theta for the resultant sits at the tail. It always sits at the tail between your two components. So when we get our final direction, since our theta is here, our final direction is going to be west, so many degrees south. Next, find the magnitude of the resultant. Well, since we've got a right angle triangle, Pythagorean theorem, and we get 2.7 kilometers, just like we did the last time we did this question. So that's the magnitude of the resultant. Of course, we have to find theta. Now, to find theta, here's the thing. Rx, technically, we actually had to calculate. So there's potential for error. Ry, also, same deal. But the resultant is even worse because the resultant was based on these numbers here. So what you try to do is you try to work with the most pristine numbers or the least potential for error. So we're going to avoid using the resultant because our Rx and our Ry has slightly better quality to them because there's less chance of rounding. So that means we have the following. If this is theta here, that's the opposite. That's the adjacent. So to solve this problem, to find that angle theta, we're going to use the relationship that is opposite and adjacent, and that is tan. And it will always, 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 always be tangent. So that's the thing about the component method. It's easy. It's predictable. It's just long. But I'm going to argue that tedious is better than difficult. So finally, tan theta is equal to the opposite side, which is our Ry over our adjacent, which is Rx. Putting in our numbers, then we get an angle. And now for our concluding statement. The resultant is equal to 2.70 kilometers. And then let's take a look. We're starting here. So we go this way first, which is west. And then we turn 41.3 degrees, 41.3 degrees, and then towards the south. So R is equal to 2.7 kilometers west, 41.3 degrees south. And since we're asked for displacement, we just replace R with D. So there you go. That's how you do the component method. So when do we use the component method specifically? So we should use it under the following circumstances. 1, if we're adding 3 or more vectors. So something like r is equal to a plus b plus c, so on and so forth, plus e plus f plus g, etc. Yeah, so on and so forth. Or 2, if we're adding 2 vectors together where both the vectors aren't along one of the axes. So rule number 1's easy. If you have 3 or more, component method for sure. But sometimes when you just have 2 vectors, that makes a triangle. We should be able to solve that straight away. But sometimes it gets a little complex. Let me show you what I mean. In this scenario here, let's say our first vector is playing nice, and then our second vector is not. In this case, honestly, it's easier to use sine law and cosine law to solve this problem. But that's because this vector here was playing nice. It's along the y-axis, which means then when you're trying to find theta, this angle, this direction theta is sitting already against the north line. It causes no problems in terms of figuring out what your angle theta is. When do I not recommend it? If the diagram looks something like this. All right, so like this one, I would strongly recommend using the component method, because take a look. So here, none of the 3 vectors are lining up nicely. This kind of, we don't know what that angle is in there. We don't know if that's a right angle triangle or not. And so we can't assume it. And here's the part that nobody likes, including me. This angle theta is only that part. So your direction for your resultant isn't this whole angle here. So you'd have to figure out angle B. And then you'd also have to find that angle in there in order to calculate theta. So then that requires you to be actually pretty decent at geometry. And in a pressure situation, you're going to make mistakes. So in this case, I would 100% just use the component method. It's always straightforward, and it doesn't matter how many vectors you have, whether you have 2 or if you have 20. It's the same technique. It's just tedious. That's all. So there you have it. So now, from now on, start solving your questions using the component method. It really is the superior way.